Now, can you see my screen? I'm not sure. Which screen
Yes.
can you see?
Yes.
Yes.
Do you see PowerPoint slide?
Yes.
Oh, we see the presenter's view.
Yeah.
Okay.
Okay, yeah, that's okay.
Okay. So welcome everyone. And today's topic is about Poisson negative binomial mixed effect model. Some parts, yes, I talked a little bit in live, what's the name of the study group? Live events group briefly, but the topic was how to decide if we should Poisson model or negative binomial model. But we didn't talk much more beyond that topic. So then today I'm going to cover a bit more than that. And this is a schedule, and today this is a topic, and then in January I'm going to touch on this topic, how to estimate relative risk when we have binary outcome. I previously I never did this type of thing. I always showed odds ratio, but after I came to Salvador, there was several requests to convert, odds ratio to relative risk. So I tried to cover this topic, and then from February we move on to longitudinal analysis. So up to now we are working on cross-sectional but clustered data, because records are clustered within city, within country, etc. But next time we are going to add one more layer when we have data of multiple years, how to handle them. And if there are any topics in your mind which are not listed here, please let me know. And today, this is today's objective. Again, well, we are going to touch on this model and how to do model fitting and also checking. And today's example data is, well, it's a simulated data based on cerebral mortality data set from Colombia between year 2014 to 2016. And this is account data for 35 cities for 3 years, stratified by sex and age. And the number of record is 3,780. I think, and then these are variables in the data set, but I think it's better to show actual data set. Can you see the data?
Yes.
Can you? Maybe it's a little bit small. So each row represents one city of one specific year of one sex of certain age category. And then we have four age-related variable, and this shows number of deaths that were registered, and population, well, official population of this age group, age 0, for example, the first one, and adjusted population. Some countries have 100% death registry, but some countries no. So we have another variable for population that account for under registration of death, which is calculated by some different algorithm. And pop L1, this is a population at L1 AD. So this is constant if the records belong to the same city. In this case, city 1 have always this number of population. By the way, this population, these are per 10,000. Okay, so I divided actual population. I divided actual population by 10,000. And this is a logged version of this variable. And this is about the data set. Do you have any question about the data set? Nope. Okay, let's go to the next one. And today's study aim is, well, I made it simple. Usually it's more complicated, but for this presentation purpose, I made it easier. So we want to assess the association between city population size and mortality, but after accounting for sex and age in Colombia 2014 to 2016. And I have a note, and I checked different countries, and I see somehow different pattern in terms of association between city size population and mortality. So what we see is not something we can observe in other countries. So keep in your mind. And when I checked Chile, I didn't see the similar pattern as Colombia, for example. And the equation-wise, this is a it. So we have city-specific intercept plus for city population size. By the way, I stands for I city and T stands for time T. So logged counts, logged mortality counts at city I at time T is given by this equation, which is city specific intercept plus term related with population size, which is city and time dependent, and sex, age, and their interaction term. Well, there's a reason why we include interaction term between these two terms, plus offset term, because the number of deaths is going to be larger if the city size is larger, and if the population in the city is small, we expect small number of deaths. So here we need to include this what we call offset term. So we don't see any coefficient in front of it, and we include offset term as described here, log of adjusted population. You see adjusted here because of the reason I explained. Some country doesn't have complete death registration, so we have to use an adjusted population. Do you have any question about this? And when I first studied Poisson model, I never understood this offset term, but now I do. And it may take some time to get what they mean. But anyway, you may be familiar with this. So exploratory data analysis before we go on to the modeling. This is a cross tabulation which shows number of records for each category by sex, age, and year. And you see 35 in all the cells. This means that we have 35 records for each cell, with for 0 category, 2014 and male, we have 35 records because we have 35 cities. So this means that there are 108 records, which is given by, we have 2 sexes, male and female, and 18 age categories, which is seen here, times 3 years from 2014 to 2016. And this 108 records, they are correlated because they belong to the same city. And this is a correlation structure we need to account for. And this is the reason why we use mixed model. And the same structure of the table, but now these numbers shows the minimum number of deaths in each category. Why am I doing so? Well, we talk about sample size many times, because if the sample size is too small, our estimation is going to be very unstable. And in case of when we use count data, it doesn't, this variance or standard error, they are associated with the number of events, not the number of population. Even if the number of population is huge, but the number of events is very small, the estimate is going to be unstable. And this is one reason I usually check this minimum number of deaths. And how to, well, we are going to do regression model, and there are mainly two ways to, two options for regression analysis. One is we calculate rate, and we use linear regression model. Well, we take a log of the rate, and then we connect with other covariate using linear regression. And the other is we use model that is for count data, Poisson or negative binomial. And when we do analysis using linear regression, but using log of rate as outcome, we have to be careful because log of 0 is not defined. It doesn't exist. So for this reason, well, if this is the case, what we do, we may aggregate. We have these tiny little cells, but we may aggregate so that we don't have 0 counts, so that log of rate, log of mortality is always defined. Or instead of linear regression, we can use models or regression models that is specifically for count data, which is Poisson or negative binomial. And now we move on to the assessment of mean component and mortality versus city population size. This is association we are interested in. And this is a plot. And on the vertical axis, we have mortality rate per 10,000. And you notice that it's on the log scale. And on the horizontal axis, I took population size. And this is also in log. This is also on log scale. I'm doing so since there are, I think in many other countries, we have mega cities. And if you don't use logged scale, they're going to be far away. And then they're going to dominate the slope. And this is what I want to avoid. And this is the reason why I'm using log scale, well, logged population instead of original population size. And the red line shows lowest curve, and blue line shows linear fit. And it seems to me, well, for my eyes at least, association is roughly linear. So I'm going to use, well, log transformed population size in this analysis. And we are going to use log 2, not usual natural log, not log 10, because log 2 is somehow, by using log 2, it's easier to interpret the coefficient, which will come later. And next one, well, we also want to assess the association, observed association between mortality and age. And well, Colombia is not exceptional, and we always see this type of pattern. Well, we have high mortality for infant before age 1, and then it drops, and then it starts moving up, and after age 50, the mortality starts moving up. And the question is how to model age. In this case, we are going to use all population not only adult, but also infant, well, but also children. So we have to think about how to model age in the equation. And in many cases, people are very interested in small, well, infant or small children, or we are interested in adult population. In this case, we may be able to use age as linear term, or one we may have some twist, and then we may include something so that we can model age. We can model this curved trend for age. But in this case, it's difficult because it's going down and then going up and then go plateau and then start moving up. So how to do so? I think the best way could be use of categorical variable for age. And also, we have 18 age categories, and age is not our main variable we are interested in. So we may group them for adjustment purpose. And in this analysis, I grouped age categories. Well, I left age group 0, age group 1 to 5. Afterwards, I grouped three age categories together. And also wanted to know if there are any difference in pattern between male and female. And this one shows median sex and age specific mortality. And blue dots show male, and red shows female. And this is also typical pattern, and male tend to die more among young age group. And then afterwards, well, the difference between male and female, they look similar. So since there is a difference between male and female in different age group, so we may consider including interaction term between age and sex in the model. Or, well, we can consider stratified model. Well, we do analysis for male only and female only. But especially when we have other potential confounders that may have different effect on mortality between male and female. And in this case, we may do stratified analysis because we may not be able to include all interaction terms in the model, which is going to be complicated. At the same time, in this case, since we are interested in the effect of city size, and at least I didn't expect the association of city population size differs between male and female for total mortality. Next, about the assessment of variability, and this is also somehow difficult thing for assessment when we deal with count data. Well, when we have continuous outcome, well, we can use box plot. By the way, this plot shows the mortality rate by city, from city 1 to city 35. And when we have continuous variable, we can use this box plot to see what is within variability and what is between variability. Well, within mean within city variability, and between mean between city variability. And with this plot, we can see only between city variability, but we cannot see within city variability. And within city variability, this is something difficult to measure. And then yeah, it's somehow difficult. Well, we may think that one person have probability of being alive or being dead, and then we start modeling. It's possible, but at the same time, it's somehow difficult to know what is the variability within city. But anyhow, this plot shows, well, this plot gives us some idea how mortality rates fluctuate between cities. It seems that it's kind of a, I didn't look at this graph very carefully, but it's very fluctuated. I mean, the mortality differs double. Well, some city have 40 and some city have 80. But anyway, this is what we see. And we start moving to regression analysis now. And here it comes the difference between Poisson and negative binomial models. We have two options for count data. And the question is which one we should use, Poisson or negative binomial. And these are two assumptions of these two models. For Poisson, we assume that expected variance is equal to expected mean, and variance is a square of standard deviation. So this is assumption when we use this Poisson model. And in negative binomial model, we assume this one, expected variance is higher than expected mean, which is described by this term, over dispersion. And you might heard this term a lot of time. And then how to assess these things? There are three ways, as I mentioned, as I wrote here. And first option is we just calculate sample mean and sample variance and compare these two and to see if they are similar or different. And this is what I get. So I grouped the data set so that one row represents one city of one specific year. We have 35 cities for 3 years, so we have 105 records now. And I calculated the mean and standard deviation variance and minimum maximum of mortality rate. And mean is 59 per 10,000. And variance is, well, it's much higher. It's double of 58. So this indicates that there is over dispersion in this data set, which means that better to use negative binomial instead of Poisson model. Another way is we just fit the model, or we assess if there is over dispersion, and we assess statistically. And well, this is a result. And well, this p-value is quite significant, which means that there is over dispersion. And this is another sign that we better use negative binomial than Poisson model. And the last one is we can superimpose the distribution of Poisson negative binomial. And the histogram shows the distribution of the observed rate. And the red and blue curves shows fitted distribution. One is Poisson and the other is negative binomial. And well, my impression was somehow it was difficult to say. Well, Poisson model maybe fit better capturing this peak around this model. But here it's underestimating this area especially. And in case of negative binomial, it captures these rates, although it didn't capture this peak. So there is somehow uncertainty, which is better Poisson or negative binomial. But eventually I decided to take negative binomial. One reason was the Poisson model didn't converge. So there was no option to use. No option to use a Poisson model. And my recommendation is whenever we do not whenever we do. When we do regression model, we can add this robust variance components. Have you ever heard about it? Yeah. By adding, if we misspecify, if there is any misspecification about variance, it's going to be fixed. So I usually use that one as a safety net. And also we know that model is never correct. And well, for the analysis, what shall we do? And these are two equations. Well, I want to try at least these two models. One model, I included only population size as covariate. And the last one is offset term, which we have to include yes or yes in any cases, because the death count, y is the number of deaths, which totally depending on how many the population size. So we have to include this one. And also we have city specific intercept, which is also necessary because we are using clustered data set or correlated data set. And the final model, it includes these terms, sex, age, and interaction term between sex and age for adjustment purpose. And this is a result of an adjusted model. And the number of observation is the same as the number of records we have. Well, this is just to make sure that no records were dropped in the middle. And the number of group or number of cities, 35. Yes, this is what we expected. And we have 108 observation per city. 108 is given by 18 age categories times 2 sex times 3 years, which is going to be equal to 108. So this is what we expected. And all cities have the same number of records, 108 maximum, 108 minimum. And well, this is this number relative risk of 0.97. This is what we wanted to know. This is a coefficient, well, exponentiated coefficient for this term, log 2 pop L1. What was it? This is a population size at L1 level, which was log transferred using base 2. So what is the interpretation of this? Doubling population is associated with 3% decline, 3% coming from 1 minus 0.997. 9% decline in overall mortality rate with confidence interval of 1 to 5. Well, 1 to 5 come from here. So 1 minus 95, which is going to be 0.05, which is 5%. So this is 5. And here 1 minus 0.99, which is 0.01, which is 1%. So this one comes from that part, and p-value copying, well, by rounding 0.017, we get p-value of 0.02. And this alpha, well, this is logged alpha, and its confidence interval doesn't include 1, so it means that there is dispersion. So it's fine to use. Well, anyway, this is just checking. Well, it means that there is that assumption that mean equal variance doesn't hold in this data set. And the next one is adjusted model. So we have a lot of coefficients here for age term, sex term, and interaction term. But we are not going to focus on these numbers because we are interested in this, the effect of population size at L1 level. And well, the exponentiated coefficient changed a little bit. Now it has more effect after adjustment. So now when interpret this one, doubling population. So doubling population means, say population was the difference of population between 10,000 and 20,000, or from 20,000 to 40,000. So this is the meaning of doubling population. When the population doubled, the effect of doubling population is associated with 5% decline in overall mortality. 5% decline coming from here, 1 minus 0.95, which is equal to 0.05. So it is 5%. And with confidence interval of 2 to 9% with p-value of 0.003 in adjusted model. Do you have any question about this? No.
Goro, I have a question regarding the category of sex male, because, for example, we think no, the data shows that males die more than females. It will be more interesting to put males in here, or no?
What do you say? Sorry,
instead of males. To use dummy as category the males.
Since the line was not that clear, but this is a effect of age among male, and the reference category is age between 5 to 19, and this is effect of female, meaning, well, women or female was 0.43, so it means that 67% less in mortality as compared to male among reference population, meaning among population between 5 to 90 years old. And this is an interaction term between age category and male, between age category and sex. And yeah, so I think this is what we see. Well, we see somehow higher mortality among male in younger population. This is reflected in this number, I guess. So it says that 0.66. Well, women is likely to die less as compared to male, and this is a ratio. But I'm not sure if I'm answering to your questions, Firmino.
I think so, because, for example, in the term of females, I don't know if we change it for males, the relationship between the death and the population will increase more, or no? Uriel, did you understand?
Not really.
Não. Se, por exemplo, ele fizesse, ao invés de mulheres, ele botasse aqui o sexo homens, porque homens morrem mais do que mulheres.
Ah, tá, mas aí ia só ser o contrário do coeficiente. Ao invés dele estar menor do que 1, ele fica maior do que 1.
Ah, ok, entendi.
Goro, he's asking if it would be more sort of intuitive to use the males as a reference, I'm sorry, the females as the reference category. Because then the coefficient, the estimated coefficients would be with respect to the males. But what I'm telling him is that instead of having an rate ratio which is smaller than 1, you would have a rate ratio which is greater than 1. So just a matter of, who's the reference in this case.
Yeah, and also, as you know, in Salvador, we have a variable called male, which is coded as Firmino mentioned. Well, 0 female as reference population and male as a how to say, comparison group. And
Yeah.
in my case, it's opposite.
Yeah.
Okay, I understood.
Yeah, because that is this is my preference, and maybe I should use a male instead of sex. Anyhow, but if you are going to, well, I didn't make a presentation table. Well, this is just output from a statistical package. And when we want to present sex and this area, age and sex association, I strongly recommend to produce for male and female instead of showing effect of male, effect of sex, and effect of interaction time. It's somehow difficult to digest. And this is the assessment of shrinkage, which always I talked about previously. So the blue dot shows observed mortality, and these are pinkish dot. These one are estimated mortality from, or estimated or predicted mortality according to our model. And this horizontal line shows overall mean. So as you can see, model-based mortality is much closer to overall mean always. So these are observed, and estimated mortality is much, I should say, they move towards the overall mean. And having said that, I wanted to confess, and this is why I wrote in this red. And if you recall, the overall mortality was around 50, but now it's much higher. So I wasn't sure why I'm getting this number, and I tried to figure out, but I couldn't before this presentation. So I'm going to look at this one more in detail, and I may have updated version of this slide later. But anyhow, the shrinkage, well, what I wanted to show is, well, the shrinkage always happens when we use mixed effect model. And model checking.
I'm not sure what happened in your case, but usually when we do descriptives sort of by categories or by age and year, and you see that the means are unusually high, it means that instead of taking the mean across categories, usually means that you're summing across the categories. So it might be that, instead of taking the mean across categories, you might just be summing them. So you would have an accumulation of the normalization that you're doing, which is 10,000, something like that.
Yeah, and more detail, and when I use a Poisson model converged for the no model, and the Poisson model gave me around 50, which was very close to what I observed. But if when I use a negative binomial, it was higher. So I was not sure why it is.
Yeah, that's weird. Might be the over dispersion, but
yeah, this is what I thought. And also this also the mortality is very different across age group, and this might be the effect. But yeah, I was not able to figure out why.
this happens a lot.
I want to have very clear slides without any doubt, but yeah, I couldn't find out before this meeting. But at least I mentioned about it here. Okay, And the model checking assessment can be done by repeating the same or similar assessments method for exploratory data analysis, but now based on predicted probabilities. Not predicted probabilities, sorry, this is typo, this is predictive mortalities. And this one shows the association between mortality and population size. And the blue dot shows observed mortality, so putting 3 years, and 1 dot represents 1 city. And pinkish dot shows the predicted mortality from the model. And the line you see, these are lowest curve. And I see similar pattern, which I was comfortable, but yeah, with somehow a little bit of difference. I'm not sure if I should say a little bit or there is a big difference, which I do not know, but which I observed. And the reason, again, I was not able to identify why there is a difference between them, or if the difference is somehow we can ignore. But I have uncertainty about it. And this one is where we also modeled sex and age. And by age group, I used 1, 2, 3, 4, 5, 6, 7, 7 age category in the model. And you see that in most of the age category, we see the overlap between this blue dot and pinkish dot. So I'm happy about this model fit to the actual data set. I think this is the end. Yeah. And so we reviewed today how to do model fitting and checking for model Poisson and negative binomial fixed effects model. And principally, the process is very similar to those for the linear mixed effect model, although what we can do for data exploration and data checking is somehow limited as compared to the case of linear regression model, because the outcome is counts. And then lastly, I probably modified and add something on this slide, and I will inform you if slides are or codes that are uploaded are changed to you. Do you have any question about the presentation? I think many of you.
Just one question about the when you test the 3 different ways to the graph.
This one.
Yes, this one. Usually you select one of these, or you try to make the 3 options.
Good question. And I think we can ask other investigators, because many of us have done this regression model a lot. Myself, I do everything. And well, I do this one, the first one, because it's easy. It's very easy to assess, and less effort is needed to do assessment. And the second one is also kind of easy, well, depending on the package you use, and then the package will tell you if there is over dispersion, yes or no, using p-value. But these are very numerical, and sometimes numbers are representative of many aspects of data. So always I do this graphical assessment. So in my case, I always do this number 3. And then also I would do 1 and 2 to make sure. Yeah, this is what I usually do. And I wonder if others have any comments about it. Uriel has a lot of experience with this.
I do all of them, as you said. I mean, the more information you have, I mean, is usually the better. You can also do a likelihood ratio test between Poisson and negative binomial. But as Goro said, this is usually contemplated. It's usually done by simply testing the log of alpha, which is the negative binomial over dispersion parameter. So it might not be necessary to do a likelihood ratio test. Sometimes we see that there is a strong association between an exposure and an outcome, and this is mainly due to the overdispersion, because when you have overdispersion and you don't account for it, the standard errors are usually smaller than they would be. So if you estimate a model and all of your associations are too significant and in the expected direction, then you fit the negative binomial model and it still converges, but things don't look so nice as they did before, then this also might be it might be that you have over dispersion in your model as well. So this is sort of an empirical type of evidence that we already do.
Also, yeah, we have option to use Poisson, and always we use a robust variance estimation. We couple these two together so that to avoid this type of problem.
And thank you.
Thank you, Tanya, for your question. Do you have any question? Okay, I waited for some seconds, but I didn't hear anything. And well, if you have any questions, please let me know or let Uriel know. And Filomena knows, and they have a lot of experience with this. And was, as I mentioned, schedule was the next time. It's going to be around the middle of January. Well, many of you may be on vacation during that time. I'm not sure. In Chile, Brazil. I'm not sure, Larissa. I'm not sure where you're from.
In Chile, we have vacations on February.
Okay. Yeah. Anyway, the session will be recorded, and you can listen when when you have time. And if you have any topics in your mind, please let me know.
Goro, the next year, so the sessions are going to be on Friday. No?
On Friday, the same time.
Okay, perfect. Thank you.
Okay, this is a end of today's session, and for this year, and I wish you Merry Christmas and Happy New Year, and I will see you in year 2022 if I don't see you in any other meetings. Bye, Sarulbal.
Thank you, Goro. You too.
Thanks, Goro.
Thank you.
Bye, everyone. Happy holidays.
Bye.
Thanks. Bye.